Okay. Thank you. I hope everyone can hear me.
Yeah. Yes.
And I'll remove your faces and go to my presentation here. So please interrupt. Okay. Last time I titled my presentation "The Development of MERMAID," and I walked you through it. I will not repeat very much of it, but I'm going to tell you about the various things that we have done with it. And so I want to call it 20,000 miles or leagues under the sea with a fleet of seismic robots. And like last time, of course, I need to acknowledge a number of collaborators. In no particular order here, Joel Simon is a postdoc. Pete Pipatratanporn is a student. Guus Nolet was my postdoctoral advisor. Jessica Irving is my faculty colleague. Yong Yu is an assistant professor at the SUSTECH. Lucia Gualtieri was a postdoc, is at Stanford now. Etienne Bachmann is a postdoc at Princeton. Jeroen Tromp is my faculty colleague. And then John Chen from SUSTECH is also very much involved here. So I'll divide this presentation into three scientific things, and one will be about earthquakes, and that'll be in this magenta color, and one will be about microseisms, and that's in this blue color, and then the last bit will be about volcanoes, which is in red. So, and I'm going to begin with the conclusions such that you have, you know where it's going, and you know what the end of it will be. So first of all, of course, land-based seismic arrays need oceanic counterparts, and MERMAID is one of those. And I made the point last time that MERMAIDs record very many earthquakes, and today I will tell you a little bit more about why and where and what we're doing with that. So this is part of the EarthScope-Oceans consortium and the SPPIM project, the Southern Pacific Plume Imaging Mantle. And we are busy assembling a vast database of tomographically useful travel times from global earthquakes. Our common target is the plume-rich area underneath French Polynesia. Now, then about microseisms, I'll tell you about what MERMAID is recording when it's not hearing earthquakes, and that's a lot of noise of a variety of descriptions. And first of all, I'd talk a little bit about how what we hear at 1,500 meters under the water is a clear copy of the signal from oceanic surface forcing, which means that MERMAID is now an environmental sensor that hears what the waves are doing. And then I'm going to digress a little bit and say, well, that's sort of a secondary microseism process that generates Rayleigh waves by the motion of the Earth, of the ocean onto the Earth, was well understood. It's an old mechanism that was understood in the 50s and 60s. But I'll digress and I'll talk about how we also hear on land-based stations love wave variety, so transversely polarized type of waves that are also driven ultimately by the ocean in a mechanism that we have recently elucidated. And then in red here, I'll talk about the noises that they're not earthquakes and that they're not ocean wave driven, but that they're rather coming from volcanoes, which we hear multiple times, but that we very specifically are trying to hear when we tuned in to the time that the Hunga-Tonga Hapai eruption happened. So a little bit of a review from last time. I mean, the big picture here is that when we're dealing with earthquakes, we're dealing with plate tectonics. And when we're dealing with plates, we're dealing with plate boundaries, where, of course, the earthquakes happen. And then we're dealing with the inside of the plate, where things like ocean islands happen, like here, the Hawaiian Emperor chains, which are by themselves, by their very presence, indicative of something that's going on, most likely in the mantle, that we want to figure out why that's there, what it's made of, what its shape, its structure, and evolution are. And the dynamical interpretation of things like Hawaii is, of course, as a hot spot, which is a surface point, but that is underlain in a hypothetical model of a large-scale upwelling that we call a mantle plume, and the plates move over it, and so the plume punctures and makes ocean islands. And you'll see here not to scale and question marks, and so the rest of this cartoon is really not filled in. This is a sort of a typical textbook cartoon, and trying to find out what's going on in the lithosphere and mantle using earthquake seismology is the object here. So last time I sort of gave you my quick tour, and just keep in mind, we want to know what the temperature is of the rocks in the mantle. We want to know what they're made of. We want to know how they transform through phase transitions and so on. And ultimately, both those things map into seismic wave speeds that we want to find the three-dimensional variations of. So that's for earthquakes here. And in 5 points here, measuring seismic wave speed. Anomalies means you need an earthquake as a source, energy at a point in space and time. You need seismometers that receive it, and that'll give you the wave field, point-based time series, records of ground displacement. If it's an anomaly, you need to have a reference model with respect to which it is. And so we have many of those reference models, many good ones that to first order describe the first order structure of the Earth. We need to have lots of computational resources to be able to do all the computations. And even if it's just first arriving waves, or whether we're doing full waveform inversion or surface wave dispersion analysis, we have the capability these days to compute what the wave field will be like for a given earthquake. And then finally, we need to make some sort of measurements that tell us that we don't know everything, and that we need to assimilate that. We need to invert for the deviations in order to reconstruct the 3D heterogeneity that are the object of seismic tomography. So here, when MERMAID, I told you last week, this is really about putting receivers in new places. If I go on in the geodynamic evolution here, then the big picture here, 400 kilometer depth wave speed anomalies from a tomographic model made by Ebru Bosdag, centered on Polynesia. The Pacific superplume here, the red areas are where the wave speeds are thought or known to be slow, and by inference the material is less dense, and by inference it is hotter and buoyant and rising up. Here's another popular picture. This is from the work of Maria Tsek-Mistrenko and Karen Zigloch and others, where they went to the Indian Ocean, around La Réunion, the hotspot. And the picture is complex here, but that's precisely the point, is they are imaging a whole sort of set of tree-like plume structures in just one example here for me to tell you that multiple places on the Earth are of great interest, both geodynamically, geologically, and seismologically, and that when you put new instruments in new places, you find new things. So our big problem for now is we never have enough earthquakes. We definitely don't have enough seismometers. And even if we try, we really only have the beginning of an understanding of what 3D Earth is really like. And that's especially true for plumes because they are slow wave speed anomalies and they tend to divert the wave field away from them, unlike, say, subduction zones, which whose imaging is ultimately a little easier, and they're also the source of all these earthquakes. So I'm skipping over MERMAID 1. I go straight to MERMAID 2. This was I'll just show you 2 or 3 slides about the only science project of the tomographic variety that MERMAID 2 did. And it went to the Galapagos. So this was 11 mermaids, 2 years. And I'll show you the tomographic model that we were able to derive. And I'll also tell you that it ultimately was in need of improvement. We did not have enough instruments. We didn't have enough time. And as you can see here, the dots are the surfacing points where mermaids ultimately reported earthquakes. And you all know that we really would have liked a more symmetric, more spherical distribution of earthquakes all around the Galapagos archipelago so that we would have more uniform coverage and better aperture of this array. But this is what we were able to do with second generation MERMAIDS. Still a very large data set. And here are two cross sections. This paper was published in Scientific Reports with the lead author, Hugues Nollet. And so here are two cross sections of wave speed anomaly through the, both of them go through the Galapagos hotspot there, but they're going in different orientations. And I'm going to try and pick my pen here and see. So here is Galapagos in both places. And here this tells you, the bottom tells you what the cross-section is like. And the cross-section deviates, as you see, a little bit from a straight line in order to get the prettiest picture. So this is a little trying to represent the model in its most advantageous way. And what we do want to see is we want to see the beginnings or the outline of something that does appear to feed the archipelago from a rather large depth where the structures appear to be continuous, maybe branching, but still there are indications of low velocity anomalies. Now, this paper, you could, it's been published, you can read it, and of course I'll be the first to admit that we really wish we had had more data. So I think we made important progress on resolving the Galapagos plume underlying the hotspot, but really ideally we were dreaming of a bigger data set. And that's precisely what we went and tried to design the third generation MERMAID here. That is the credit to Jan Hello, the engineer who worked at Geoazur in France and with the company called Océan. And so they built this working model that you can all buy now and that many people have bought to record earthquakes worldwide. And the main benefit here is that it is a 5-year autonomy. And so the instruments, the first ones, which we put out 3.5 years ago, are all still working and reporting earthquakes. I showed you this last time. It's essentially a hydrophone and an antenna that keeps time, keeps the location, and that we can talk to, and that it reports its own earthquakes, but we can also dial into it and get more. So where is MERMAID now? You can find this out live on the website, www.EarthScope-Oceans.org. You can click on where they are. You can see their trajectories, and you can actually get all the metadata already. And you see here the institutions that contribute to the array. The biggest player in town is SUSTECH. Here is John Chen. And we have now also, or he rather, has now also gone to the South China Sea. And then there is 6 MERMAIDs in the Mediterranean that are not on this map here because it's a little bit too far to the east. So what we are currently doing, and this is ultimately the last I'll say about the earthquakes, is we are just detecting data. This is a picture that I took when I put 11 MERMAIDs out from Princeton, and that's the view from Tahiti on the island next to it called Moorea. And in older tomographic models, like the one from Pucao in 1992, we are seeing, of course, the hint of an upwelling below and an interpretation in this dynamical way, again, of a rising large plume. But that's, of course, showing you not all the detail that it must have, because this is ultimately 30-year-old result. But that's why we're there, to try to refine this picture under this important region. And so I'll just show you a couple more cross-sections through other models that were made with global data and not MERMAID data. Here is a cross-section through Samoa, an island in the US sphere of influence here. This is a north-south cross-section, and then an east-west cross-section that shows you Samoa again, and then also Tahiti, which I just showed you, and the Marquesas. And here, this tomography done by French and Romanovitz and others is showing you zones of low velocity material that appear to be rooted at the core mantle boundary, and then upwelling towers of plumes that appear to branch out. And so it is this sort of analysis that we want to get a lot more data into so that we can get up close and do tomographic modeling. Now, I showed you data and data quality last time, so I won't repeat it. I'll just say that for, as far as these earthquakes are going, we just keep at it. This is a picture of 16 Princeton mermaids and their trajectories here. Every time they come up, they report a few earthquakes. They come up every 6 or 7 days. They live about 4 to 5 years. They haven't died yet. They're reporting data every day. And we look at that and we measure that. We identify the earthquakes. We measure the travel time. We measure the travel time anomaly. We do the correction. And it just goes into the database that in a few years we will have enough to really make a dent into this region. So the magenta theme here, the earthquakes, and including what I said last time here, that's essentially a done deal with MERMAID. We are doing that. We're in Polynesia. We are making a data set for tomography. The data look very good. There's many of them, and that's an ongoing project that is too early to discuss the results from in detail. So the second theme that I want to talk about is what happens when there are no earthquakes. And so normally, we do not recover MERMAID because it just sends all those earthquakes. But now and then, we are able to recover one. And once we recovered one when we were already in the area. And so here, I'll report on what happened when we managed to pick one MERMAID out and read its entire 1-year data buffer. So this is MERMAID 23. And it was put out in September 2018 by myself around Tahiti, and it went, did all of this stuff. And then a year later, a graduate student, Lucas Sawade and Jan Hello and others on an Ifremer ship went and recovered it. And the top box is that little bit of yellow here, which just shows you how incredibly vast this ocean is. This MERMAID hadn't done very much area, but it had a whole year worth of data in it. This is a paper that was just came out in January in 2022. So I'll show you the last earthquake. This is from this MERMAID that we got. Remember, normally when we get MERMAID data, we really only get about 250 seconds, 5 minutes or so, and we're able to look in detail at the P-wave travel time and measure the deviation, and that's our input, that's our travel time residual that goes into a tomographic anomaly reconstruction. But when we have all the data, because we have the entire data set from MERMAID, this is one that it didn't report, and so it just kept recording. And so here you're seeing the entire wave frame where you're not only seeing P, but you're also seeing the S wave conversions, and you're seeing branches of surface waves coming in, and you're seeing a variety of unrelated water waves, but then at 1,500 kilometers per second, at 1.5 kilometers per second, we are seeing the associated T wave that comes from this earthquake, whose P wave and S wave we've already seen. And then we're seeing this large band of noise that appears to be not varying. It's throughout this record. And what our student here, Pete, did was find all the earthquakes. First of all, the ones that were reported. Second of all the earthquakes that were not reported. And then all the other transient signals. And when Pete took all of that out, he obtained noise curves. So here is a little calendar of January, February, March, May, June, July of that year. And what's shown is a histogram that's in color with the x-axis frequency and the y-axis the spectral density. And so every month in 3-hour windows, you have a large variety of spectrum, but they are summed up in these individual diagrams. So I'll show you just one of them. The red line is the median spectral density for March 2019. The colors are diminishing percentiles, and so the curves just about show up what happened. Now, they all look pretty much alike, and we understand them. The cutoff at the right here, that's something that we do. That's a filter that we apply to MERMAID when we report only 20 hertz data whose power has been cut, so that's not that important. In this area, this is where very often we see ships, which are also taken out of this. Then we see this large hump that I will be talking about. And then just about as we are to lose sensitivity here in the lower frequencies, we are still picking up a large hump of noise. And so what we did with this is we looked in different frequency bands and tried to explain the differences in this noise from day to day, week to week, hour to hour. So it is at this point that we need to ask ourselves, what is happening at the ocean surface? Okay, because there were no earthquakes, we've taken them out. There were no ships, there were no submarine volcanoes. It's really just the nothingness of the ocean. It's the noise of the ocean itself. So it turns out that there is an oceanographic model that's called WaveWatch, which will tell you at every 3-hour interval of the any day what the wave power is in particular set of 14 different frequencies or something like that. And so I picked out, some random day last year. And so you can download this from the website, and here is a spatial rendition of this noise. But essentially it tells you, where storms are going and where the wave height evolves. And so these are these forecasts. In fact, they're hindcasts because they're models for the past, right? So we were clearly sitting in this ocean, and we were able to look for every day of the 2019 year that we had all the noise data for exactly what the ocean model, which is also informed by observations, but no mermaids at all, was predicting. So last year was a very fitting year for this because it was Hasselmann who earned a Nobel Prize in physics for work he had done in climate. But among the many things that he did also earlier in his career was look at ocean models. And so it was Hasselmann in the 60s who ended up explaining how the ocean waves that we just saw actually couple into Earth noise that we see normally on land-based stations, but that MERMAID now is intercepting right in the middle of the water while it's floating there. So there is a theory, and it's by Longe Higgins in the 50s and Hasselmann and others in the 60s. And they prescribe the following. It tells you in the theory that the interaction of ocean waves produces nonlinear effects, whereby here in this color here is WaveWatch. This is the spectral density of one interval in time, and this is another one. I'm just showing two different examples, but let's just look on the left. So this curve here that I've just highlighted is what the ocean is doing. And the theory says that these waves interact and couple into seismic noise that should have a frequency that doubles. So if we double the frequency, of course, we're shifting this curve to here. And so now in red, the figure here is highlighting what MERMAID is hearing. So I'm not showing you the match. I'm about to show you the match, but you need to imagine that, like, I will be showing you that if you shift this to the right, these curves in many of the details overlap, both by being in the right frequency range, but also in the right magnitude, because we actually do have proper instrument response functions for MERMAID, so we know exactly what the pressure is that we are recording. So I'm going to erase that and show you when we now just ask the question, let us compare the power and the coherence of what the ocean is doing in frequency and what MERMAID is listening to, then this line here, which is the 2-to-1 line for the frequency doubling mechanism, that's where we should expect coherent behavior if the noise that is recorded by MERMAID is indeed literally just generated by this mechanism whereby nonlinear interaction of gravity-driven ocean waves couple into producing a sort of standing wave pattern that forces a sort of a type of Rayleigh wave noise motion that we know we observe on land, but that we now observe in the ocean. And that is exactly what happens. So here, this red band here around the 2.1 line, the 2-to-1 line, is showing you that the coherence between what a completely independent ocean model, hindcast model, is showing you and what MERMAID is recording for the first time in this much detail is really exceptionally coherent. And so here, Pete is drawing particular boxes. Let's just look at box B or C here that shows you in that particular frequency, when you multiply the frequency by 2 here, that you're seeing that MERMAID and the ocean are in real lockstep for an entire year. So what we take away from this here is that when MERMAID is not reporting earthquakes and is just sitting there listening, that is actually an environmental sensor that tells us something about the ocean state. And clearly we know something about the ocean state from satellites and other type of buoys and models, but that's not everywhere the case. That's not the case for certain difficulty to access latitudes and so on. And so this sort of data is just a richness that goes beyond seismology that we're excited about. So as to microseism here, this theme that I just concluded here is, look, MERMAID observes the secondary microseism and generation process in situ. We are now right there where it happens. We are halfway the ocean surface to the ocean floor, and we're hearing this process that was predicted and very well observed on land. Now, for the very first time, we're hearing this basically all over the ocean. We're very excited about that. So MERMAID is an environmental sensor, even just by looking, or rather hearing, acoustic noise. So now I want to take a little sidestep and ask an important question that is, well, look, what does happen on the ocean floor? Okay, I described to you in not much detail a mechanism that was a theoretical mechanism by which ocean waves couple into Rayleigh wave motion. But when we listen on land stations, we also hear other motions. So this Rayleigh wave microseism mechanism, it was well understood. That was this nonlinear interaction of ocean surface waves at the surface. That's the Hasselmann and Longet-Higgins mechanism. But when we're listening to land-based noise, we're also hearing transverse component type of waves. So let's try and look at microseismic noise of the Love wave variety, which is an interesting question if you think about it, because the ocean goes up and down, and that's understandable that it produces Rayleigh wave, but it's a little harder to understand why an up and down heave of the oceans should produce the sideways motion that ultimately is of the Love wave variety. So that's my question. How does the heave of the oceans, that the up and down motion, produces the sway, the sideways motion in the solid Earth? So that leads to 3 side questions. One is, well, if it's just noise, you cannot just rotate seismogram components. You actually have to think about what transverse motion is. Second of all, you have to think about the sources. But luckily, I just talked to you about WaveWatch, and so we have access to ocean models that we could use for simulation. And third of all, we have to ask ourselves how to simulate wave propagation in a full Earth. But luckily for that, we have the Spectrum 3D Globe Code, which in principle accounts for all sorts of elastic wave effects and also anelastic wave effects into an Earth that we can make realistically complex. So now this is the work of Gualtieri, and this is non-MERMAID. So I want to stress this is about land-based stations, but because it tightly puts the story into connection with the ocean surface, I want to put it in here. So when you have an earthquake and you plot acceleration on the left in one component, and you plot rotation rate along the vertical axis on another axis on the right, then when the regular earthquake waves are arriving, you have almost a one-to-one match of these, acceleration and rotation rates. And you're seeing that here as an area of a high coherence or a high correlation coefficient in time. When it's just noise, there isn't anything. When there's coda, there is some up and downs. But when the main arrivals of an earthquake happen, there is high coherence. So what when you don't know the azimuth of an earthquake, you can look for the azimuth that maximizes that correlation coefficient. So I showed you that if you know it, the right axis, then it's coherent. But if you don't know the axis, then of course that gives you a way of estimating it. And so this is now color-coded cross-correlation coefficient, where it is 1 is where the main arrival is happening. And by looking across all azimuths, it identifies exactly what the true azimuth is. So that's for an earthquake. Now, the title of this slide is that, of course, you could do that for just noise, and you can just hope for the best and see if there are coherent directions. So that's what's happening here. Now I'm showing you an example where this doesn't work. There is, on the left, no coherency of any special direction, nothing interesting going on, no special azimuths, and the plot on the right is basically empty. So that's a situation where there's nothing of any value. But now imagine that you have a noise time series and you actually can pick out a coherent azimuth. And so that's shown here. This is another example, but one where the coherence in a specific azimuth of a non-earthquake time series actually is very high. And if we make a histogram of the azimuths where the coherence is high, we are able to say, well, for this noisy time series, we'll call this the sort of azimuth at which the energy of the love wave type variety is being generated, even though, again, there is no earthquakes here happening. So that was the goal of the study, and also the result of the study. That were two papers by Lucia Gualtieri in PNAS and GGI. And we asked ourselves the question, look, nobody at the time really had a good explanation for love wave motion being generated by just noise. Remember, the Rayleigh wave mechanism was understood. So we have 4 scenarios here. A, in the top left, is a one-dimensional Earth with no 3D heterogeneity and no bathymetry, no topography. The theory should tell you there is no way that you can make any love waves. 2, B, is maybe, and those were the early indications, maybe because there is bathymetry, you are able to do pressure conversions and pressure splitting at bathymetric inclines, and maybe that is the source of love wave energy, where the up and down motion of the ocean actually hits the slopes of the bathymetric topography of the ocean floor, and that's enough to happen, make love waves. And then C is the case where there is no topography, but there is a realistic heterogeneity in the Earth. And D is the case where there is both topography and heterogeneity. So now I'm just going to give you the short version of the story. And it turns out that the picture I just showed when there is nothing to see is when there is no topography and there is no interior structure of the Earth beyond layered PREM-like structure, then you essentially get nothing. So here in this map, the colors are a rendition at some point of the ocean pressure, just to give you an idea that this is a northern hemispheric winter, most likely. I forget now. But so that gives you an idea of the heterogeneity of essentially this wave watch type of behavior. And every one of the stations is marked here is a GSM station where Lucia tried to find love waves and coherent directions. And the little bitty white things that are not showing here show you the lack of success at all these stations, except maybe here at this station in southern Germany, where you have a little bit and a little bit of this here. But the bottom line is no, you do not get significant love wave energy in a 1D Earth with bathymetry. It's not enough. There is a little indication, but it doesn't quantitatively express or predict how much we actually see in observations. To cut the longer story short is, well, we know the Earth is bathymetry, so we do need to put it on. But we also know the Earth has heterogeneity. And so in a, tomographic model, as best as we have, it's not the perfect model, but just to get enough heterogeneity, we did these simulations where we drove the wave propagation with ocean-generated wave heave noise. We coupled it into the bathymetry according to the bathymetric angle, and then we ran the wave propagation for hours on end. And it turns out that all of these internal conversions ultimately fill all the energy available slots that you have. And so ultimately, through an ergodic mechanism where all the available energy states are being filled, you do produce love wave energy. And so that is the main message of these two papers here, that yes, it's a 3D heterogeneity of the Earth, much more so than the Earth's little bathymetry, that produces quantitatively very much so in the right frequency and the right amplitude what the love wave type of energy is that we get from just listening to ocean noise on land-based seismometers. And so here for the same stations in the global seismic network here, you're now seeing the same analysis. And when these rose diagrams here show you, when they're much larger than anything you've seen, it shows you, yes, there is all of that love wave energy that is being detected using the method that I've just shown you. And it is pointing to the direction where it is generated, right? So similar analyses have been done for other types of noise, but not for love wave types. So we were able to explain quantitatively the presence of love wave, the mechanism by which it generated, the reconciliation with observations, and also the directionality that shows you where, if we just connect these things by great circles, we are seeing where those things are generated. So to me, that really ties together the story on microseisms as well. There was MERMAID and it was recording this Rayleigh wave noise, but we also had this open question on what love waves types of noises were doing. And so, well, oceanic pressure noises do generate love waves within the solid Earth, and that is primarily via interaction with the three-dimensional heterogeneity within the Earth, and in a minor way by boundary force splitting at the bathymetric inclines, because of course the Earth does have topography and there are shells and so on. So that's in these two papers. And so now I'll pick up the volcanic example. And so I'll return once more to the MERMAID 23, to the example I already showed that showed you clear P waves and clear S wave conversion and some clear surface waves and some clear T phases. But remember, this is all the earthquake stuff that Pete Prathanporn, took out of the 1 year buffer. And many, many times during that year, it wasn't just the Rayleigh wave noise, but it was also short bursts of activity. And I'm showing you one example here. This is a linear frequency scale. I previously showed you a log scale, so I'm redoing the figure here. This is the log scale, log frequency on the left and time on the x-axis. And the colors are the intensity of the spectral density at that frequency. And the right axis is a spectral density, and I showed you before the many, many, many forms of the spectral density. Well, now in this particular case, what you are noticing is that this is a time interval where right here, we're seeing a lot of activity, and we're seeing these bands or whatever it is of noise that are very different than that Rayleigh wave noise whose big hump we already just studied. That was the Rayleigh wave noise. I told you here there are ships, but yes, there are also these intervals where there is just a lot of bursts of activity. And in the paper, we list and we show them. We're basically saying, yeah, some volcano, right? Because that is a mechanism to get hydroacoustic energy in the water that is not necessarily connected to any earthquake, certainly not to a global earthquake, and that has a completely different character than everything else we are actually able to explain, such as the Rayleigh wave microseismic noise peak. So, of course, when the Hunga-Tonga eruption happened, we wondered what we heard. And we looked at our array of 51 instruments that I show here, 16 Princeton, 4 Japanese, 2 French, and all the others are Chinese owned by SUSTECH, 30 some. And the ones colored in red here were listening. The other ones were either recording something else at the surface on a descent cycle. In other words, they weren't there right at the time, but they were there at the time, but they weren't recording. I also told you that normally MERMAID reports earthquakes, but if you want anything else, you can talk to it. So right away, and it takes a while to get the full data, and we're still doing it, we started requesting data from the big 1 year memory buffer. Remember, we once recovered 1 full year MERMAID, but now we have to do it over an Iridium modem, which is a little slower. But the red ones are showing you all the areas where we were able to get data. And here is an example, okay? So here's a record section of all the segments that we have had so far. We prioritized making requests. Again, they're still going on, but we prioritized requests. So this is time on the x-axis, and this is epicentral distance on the y-axis. And so we prioritize requests along the 1.5 kilometer line, which is the water speed of an acoustic wave. And we're also trying to fill in the P and S wave time windows, and you see that some of these data are also coming in. This is what we had as of 4 weeks ago, so there's probably some new things that have come in that Joel Simon, who is doing all of this, is getting together, and there'll be slightly more soon. But anyway, if we do a traditional array analysis with those type of data, and we're saying, well, we're essentially saying, let's not use our eyes, even though I'm about to also use my eyes. And we're making a vespogram where we're stacking the signals in small increments of slowness variation relative to specific phases here. What you want to see is that the red area is the area where there was a lot of coherent energy stacking, which shows you that whatever is moving through this array is moving at a speed of about 1.5 kilometers per second with respect to the timing of Hunga-Tonga, which is not perfect, and so there is a little play here on the x-axis. Much more energy, so than any P or S, which should be coming in this direction. So there's clear indication that there is some P wave energy coming from this volcanic eruption, but collectively and in one word, most of it is strongly hydroacoustic in phase, and that's that big bullseye red dot here where the 1.5 kilometers are marked. But let's look again in the time domain, and here I'm just going to give you a few examples because that's what we're really doing at this point. We're looking and we're requesting more data, and we're able to ask questions and connect with people. Here is MERMAID 45 at 10 or 11 degrees, and we'll look at MERMAID 23. Okay, so it's 45 and 23. And let's just look. They're in the same azimuth. They're just a little more distance. So if there is energy radiating, then really what you want to look at is how much alike it is. And it turns out that when you plot the spectral density, this is a spectrogram of 45, this is a 23. I mean, you're seeing how similar these signals are both in time and both in frequency. They're just essentially delayed versions of one another. So plotting 45 right onto 23 and adjusting by 1.47 kilometers per second water speed, we're getting a mirror image here. The top is the upper envelope of 45 in red, and the blue is the lower envelope of 23. And so you're seeing that these things, these signals are like, this isn't random scattering, right? This is a source effect. This is the time series that Hunga-Tonga pumped out, and 45 heard it first, and 23 heard the same thing a little later, and then we'll leave the rest of it to further analysis. But so this, I find a remarkable, good-looking figure. So now let's look at two other ones in a completely different corridor. Here is 49. For some reason, and I'll show you where it's at, 49 heard nothing. It's a low noise, very well recorded time series that heard absolutely nothing in red here. Sorry, wrong way. 49 compared to 48, which is same direction and still close by, and it heard almost again a copy of the source signature. So there clearly is a directional effect here. 49 again, it hears absolutely nothing beyond the sounds of the normal ocean that we already knew about. Whereas 49 hears, is 48, I'm sorry, here's this beautifully pulsed signal that shows you an intricate space spectral signature that is showing in the spectrogram here. So, and here they are, right? So this is really the end of this talk, in the sense that we're just looking at it and wondering. I'm going to annotate here. Like I showed you 45 and 23 and actually 40. You see the signals are like very well propagating in this direction and very coherent and very revealing of what the source is. 48, 49, through probably propagation effects or maybe also a directional source effect or something I don't know about. One of them records almost nothing, and the other one records again a beautiful signal. Some of the distant ones hear very well, better than some of the close ones. Some of them directional ones are different than other directions, and so we're really just beginning to explore this data set, which, as I mentioned, is continuing to come in. The reason it takes a while to come in is that we have to tell MERMAID to give us data beyond the trigger data, and it only comes up every 6 to 7 days. And if there is a backlog, it doesn't want to stay at the surface too long. It'll just go and it'll send it the next time. And so we continue to make requests as much as we can, and we have about another 9 months to do so because our buffer is 1 year long. And if we can afford the telephone bill, we'll get a whole lot of data. And my message to you also is that you will have questions that I don't have answers to, that may be other requests of data can help answer. For instance, when did the eruption really start? What was the precursor a day before, 2 days before, a month before? I don't know, but if there's any indication that our direct observations from MERMAID are able to help you, then we're going to be able to make those data requests. So that was theme 3. Whatever happens to volcanoes, MERMAID, it hears a lot of them. We normally don't bother. We normally don't report them. We don't want them. We know about them. We knew about them because we had a whole year's worth of data. And for Hunga-Tonga, we specifically went and looked because that was especially well recorded. We were right there. And we were the only people to be right there because MERMAID is a unique instrument. And so the data continue to be requested, and hopefully is going to be a longer story. So if I want to wrap this up here with my 3 themes and my 3 colors on the earthquake theme, there is we need oceanic instrumentation, and OBS is phenomenal, but MERMAID is there and we have many, and that's also going very well. We record a multitude of earthquakes, thousands and continuing on, which we're using for global tomography, especially in Polynesia, but increasingly in other areas. As to microseisms, floating MERMAID also record noise. Much of that is Rayleigh wave type of infrasonic noise in this terminology that tells us about oceanic surface forcing, which we are able to link to an ocean model, and which we're also able to link to what we hear on land in terms of Rayleigh wave type of noise. And that just led to the question of, well, what is happening with the love wave noise, which we also hear on land stations? And that is that mechanism that I explained to you, where it's a combination of a minor amount of bathymetry and a major amount of internal structure that actually completely populates the energy states of both Rayleigh and love waves that we are able to quantitatively explain both in magnitude and amplitude and direction, what the observations on land-based stations have been, which was a gratifying non-MERMAID piece of study. And then finally, yes, we never thought in a million years we'd be doing volcanology with MERMAID because we were reporting earthquakes, but now we have the buffer and we can ask for it. And we were so close, we are able to hopefully bring to the community a valuable set of data that will help them, you and others, understand exactly what happened with this latest Hunga-Tonga Hapai eruption. So, earthquakes, microseisms, and volcanoes, those are all the types of science that we are able to do with the types of instruments that MERMAIDs are. And that's it. I thank you for your attention.